this expression here for the probability of measuring any particular y. And I'm going to introduce the change of variable. So instead of this heavy expression, I will, with this change of variable, I will write just 2e in theta y e. And by this index y, we recognize that this theta y depends on y. So with this variable change, everything will become shorter. And now we are going to distinguish some y's which are in some sense better than the others. And for those y's which satisfy this equation, we will call them good y's. And we are going to estimate the probability of measuring good y's. And for this expression here, if we rewrite it with the variable change, let's do it. We can notice that it is a sum of geometric progression. And we know the formula for this sum. And if we don't, we are still lucky to have it right here. So this sum equals to E A theta y I minus 1 divided by E theta y I minus 1. So this is what we have here instead of this sum. Okay, so instead of this here, we are going to write this. And I'm going to estimate this fraction for good y's. And I'm going to do this separately for numerator and denominator. And for the numerator, I'm going to write this. So it's e power a theta y I minus 1. I'm going to prove that it is greater or equal to a absolute value theta y divided by p for good y's. And to do this, I'm going to introduce the variable change to write less. So let x be a theta y. And let's take a closer look on this expression. So it's absolute value e xi minus 1. And I'm going to use the Euler's formula. So it is cosine x minus 1 plus I sine x. Now, instead of this absolute value, I'm going to write square root. So it is cosine x minus 1 squared plus sine squared x. And when we open this square, we get square of cosine, which among with sine gives us 1. Another 1 we get from here, so it will be 2 minus 2 cosine x, which goes from this scope. Okay, does not look good yet, so we are going to employ the formula for the cosine of double angle. Instead of these 2 here, we are going to write 2 cosine squared x divided by 2 plus sine squared x divided by 2. And instead of 2 cosine, we are going to write 2 cosine squared x divided by 2 plus 2 sine squared x divided by 2. So here I employ the formula for the cosine of double angle. And this looks now better because these cosines, they go away, and the only thing left here is 4 squared sines. So we can write that it equals to 2 sine modulo x divided by 2. So this inequality here we can rewrite now as 2 sine a absolute value theta y divided by 2 is greater or equal to a theta y divided by p. And we can now remove these 2's. And let's take a look at these for good y's. So this is the linear function on the interval from 0 to pi. So here we have 0, here we have pi. In 0 it equals 0, and in pi, when a theta y equals to pi, it is pi divided by pi, so it is 1. Okay, linear function. And this sign here, when a theta y equals to 0 also equals to 0, and when it equals to pi, then sine of pi divided by 2 is also 1. So in the ends of the intervals, these two expressions are equal. And on this interval, sine is a convex function, so it goes like this. And on the whole interval, it is bigger than this linear function. And we proved our inequality for good y's. So we have estimated the numerator. Okay, we put this achievement here, and we are going now to estimate the denominator. And I'm going to prove that this denominator, 2yi minus 1, is less than equal, less or equal to theta y absolute value. So if we estimated that numerator is bigger than something, then we have to prove that the denominator is less than something. And how we are going to prove this? Well, let's see this geometrically. Here's the complex plane, so here we have y, here we have 1, and this unitary circle, not very pretty, on the complex plane. And we have this angle theta y here. And this expression, this absolute value, is, here we have e in power theta y I minus 1. So this expression on the left is the length of this chord. And this expression on the right is the length of this arc. So what I'm trying to say is that the arc is longer than the chord. And it is always true, so I believe I proved this. Now we have both estimations here, and we are ready to estimate the whole thing, this probability. So it's going to be greater or equal to 1 divided by a n, and instead of the numerator we take this, so it's 4a squared, absolute value theta y squared. Here we have pi squared, And here we have just theta y squared. This goes away, this goes away, and we have this. And this expression here, it's approximately 1 divided by r, as we remember, so I'm going to write it. So this is approximately 4 divided by p squared r. And this is our probability to measure any of good y's. And why these y's are good and what to do with this probability, we are going to discuss in the next episode.